The objective of this experiment is to use an FPGA as a form of a decoder for a 7-segment display. The decoder will be used to convert binary code into corresponding numbers that will be displayed on the 7-segment display. The theory is that if we use a field programmable gate array, also known as an FPGA, for our subsystem 1, we can program it using binary code to achieve our 7-segment display. A FPGA is an integrated circuit designed to be configured by the designer. The FPGA configuration is generally specified using the hardware description language, HDL. FPGAs contain an array of programmable logic blocks. These logic blocks can be configured to perform complex combinational functions. For our experiment, we will use the logic blocks as a simple 4-bit flip-flop register. These flip-flops will read through the code and determine which number will be displayed on the 7-segment display.
Subsystem 2 then uses combinational logic to determine which LEDs on the 7-segment display would receive power. The truth table shown here displays what the expected 7-bit output is based on the 4-bit input from subsystem 1. You may have noticed that the input in decimal is not what is being outputted. Instead, for the most part, the input values are based on what LEDs are not lit up. For example, if A on the 7-segment display is missing, a 1 would be placed in the most significant bit, and if G is missing, a 1 would be placed in the least significant bit. What this does is make simplifying the logic easier. Using Karnaugh maps, the outputs are reduced to having much simpler logic algorithms than would be the case if minterms were used instead. Likewise, by using the system mentioned above, this is reduced even further by having the K-maps align with a pattern, which even allows some outputs to be reduced to only a single input. Here is the final logic diagram of subsystem 2.
For subsystem 3, we will use 2 NOT gates to act as a grounding component for the 7-segment display. The reason we are using 2 NOT gates is because each NOT gate only has 6 outputs, and we have 7 inputs that we have to put in. Since the 7-segment display has no ground and the diodes only have output, that is the reason we are using the NOT gates. So in theory, if we connect the output of the NOT gate to each diode, then the NOT gate will act as a current sink.
Materials list:
FPGA, breadboard, wire leads,
7-ohm resistors,
a .40 anode digit display,
and hex inverters or NOT gates.
Step 1. Place the digit display and the NOT gates on the breadboard. Notches facing left and the dot facing right. Step 2. Connected the digit display to the power bus and connected the NOT gates to the power bus and ground bus. Then connected the top and bottom power buses together and the top and bottom ground buses together. Step 3. The digit display and the NOT gates were connected with the 150 ohm resistor. The output pin of the NOT gate is connected to one of the pins that correspond to a segment of the digit display. Here shows output 2Y connected to pin 2 of the digit display that corresponds to segment E. Now the same was done to each other segment of the digit display. Step 4. The NOT gate's inputs were connected to the digital output pins of the FPGA. The digital output pins used were 23, 26, 29, 32, 34, 40, and 50.
For the code, let's start with subsystem 1, which has a 4-bit register and a 25-bit register. The 4-bit register serves as the 4-bit input to subsystem 2, while the 25-bit register serves as a counter. On every positive clock pulse, the counter increments by 1 until the counter resets to 0 after 2 to the 25 minus 1 counts. At 0, the 4-bit register will shift to a new value based on its previous value, effectively turning the 4-bit register into a 4-bit flip-flop register. Starting at the 7-segment equivalent of 0, the system will transition at every 0 on the counter until it hits the 7-segment equivalent of 9, and then the next state will then be the 7-segment equivalent of 0. The primary purpose of the counter is to have the flip-flop transition at a much slower rate than the 50 MHz clock pulse. Subsystem 2 has 7 outputs A to G and also uses the 4-bit flip-flop register from subsystem 1. In this system, bit 3 of the flip-flop is equivalent to W from the theory section, as is bit 2 to X, bit 1 to Y, and bit 0 to Z. Using this information, the outputs are set equal to the combinational logic derived from the Karnaugh maps in the theory section. The source file that contains the code for subsystems 1 and 2 is then implemented in the main. The outputs are declared to be the 7-bit output array pin. However, at this point, pin isn't anything. The locations of the pins are declared in a separate source file. In this case, pins 0 to 6 refer to the pins 50, 40, 34, 32, 30, 29, 26, and 23 on the actual board itself, which are then the inputs to subsystem 3.
This is how the current limiting resistor was found. It was found to be 125 ohms, so 150 ohms were used. This is a screenshot of each segment during the counter. They are inverted because they're taken at the output of the NOT gates.
Field programmable gate arrays are semiconductive devices and a hierarchy of reconfigurable interconnects that allow the blocks to be wired together like many logic gates that can be interwired in different configurations. In this lab, we use two theories for three subsystems. The first one is we use the flip-flops to store the bits of the data, which are binary digitals, and change states to verify the 4-bit inputs for 7 segments. The second one, we use the K-maps to simplify the truth table, which shows the binary digitals of numbers from 0 to 9. During the lab, because the clock pulse was moving so fast and the state changed so fast as well, that we couldn't read the number on the counter. So we control the state change by constructing a 25-bit counter that changes state whatever hits 0, and we also add the code to slow the clock cycle down. The second problem is after displaying the number, we found that the K-maps for D and G of numbers from 1 to 4 were wrong. So we adjust the code to get all numbers perfect displayed on the counters, and that's all we have. Thank our group members, Brina, Josh, and Dominic. Thank you for watching.